In this example, we are given a theorem, or a statement at least. It says the line segment that joins the midpoints of two sides of a triangle is parallel to the third side of the triangle. And we are given an image here with some coordinates already given to us. And we're asked to prove the theorem by using the image and kind of using an analytical approach. Okay? In other words, we want to use the coordinates here somehow. So what we can do, number one, we need to kind of unpack what we know, right? So what we know is that M and N are the midpoints of sides AB and AC. So M is the midpoint of BC, right? And so then let's write down the equation of the components here of the midpoint. So M, its components are then what? Remember, it's always the average of the x and the y components, right? So this is going to be 2b plus 2a all divided by 2. That's the average of the x coordinates. And then the average of the y coordinates is 2c plus 0 over 2. And we can reduce this, right? So that means that our m coordinates are, we can factor out the 2. And then this is all divided by 2. Over here, there's a 0, so we can just cancel these 2's. And our last step here, so we should be writing equal signs here. The last step then is that the coordinates of M are, these 2's can cancel, and this just leaves us with A plus B and then C. So there's our coordinates for M. We can do the same thing with N. I'll let you guys work it out, but what you end up with is that, so I'm going to darken these up. So we end up with that N, the coordinates of N are just A0. And that's done by computing the average of the x coordinate with of A and B and the y coordinate of A and B. All right. So I showed you how to do it for this midpoint. Make sure you can do it for this one. Now we want to prove that these two lines are parallel. So I'm going to write TBP, to be proved. All right. And this is that we want to show that AC is parallel to NM. All right. And we know that parallel lines have the same slope, right? So we're going to show that the slopes are equal. And we know how to compute the slopes, right? So the slopes are equal. Remember, the slope of a line is equal to the rise over the run, or the change in y of that point, of that line, right? Divided by the change in x. All right, so in our minds we read this as, we read it as delta y over delta x, but in our minds we remember this as rise over run, the amount that the line segment is increasing in height over the amount of distance that you kind of went over in the x direction to get that height, right? So let's compute these. Let's start with line AC. All right, so I'm going to write this as slope of AC. So slope of AC, well, what's it going to be? We need to compute the delta y and the delta x for each of these, right? So the delta y is going to be, you could choose either of these points to be your kind of initial point and the other one to be your terminal. I'm going to do C minus A. So I'm going to do A is initial and C is terminal. So delta y is going to be then yc minus ya. I'll write it like this so we know exactly what's going on. The y component of the C is 2c. Different C, by the way, right? This is capital C and lowercase c. So just be careful. Minus the y coordinate of A is just 0. And so the change in y for line AC is 2 times c. Right? We need to do the same with x, right? So delta x is going to be xc minus xa. Now, these have to be in the same order, right? So if you chose to do A minus c, you have to do A minus c down here. If not, you just keep going. So here we do the same analysis, right? So up here, the x coordinate is 2b minus 0. And so that means our delta x for this line is 2b. And we can put it all together then, right? So our slope for this line is delta y over delta x, or 2c divided by 2b. And this will reduce, right? We can cancel the 2's and we end up with c over b. So there's the slope of line AC. Now we need to compute the slope of line NM and see what we get, right? So step 2 here is the slope of line NM. Same deal, we can choose either one, either point M or N to be our primary point, and then the other one to be the subtraction. I'm going to do m minus n. I like to do the higher one minus the lower one. You could do this however you want though, as long as you stick with it, right? So in this case, I'm going to do y sub m minus y sub n. All right, this is a capital M, even though my penmanship is not good. So the y component of our m is c, and the y component of n is 0. So this is going to be c minus 0. So far, so good. That's just c, right? Then we compute our delta x. Same deal, right? It's got to be x sub m minus x sub n. Because we already chose that order, you have to stick with it. So now we go back up. The x-coordinate of m is a plus b. The x-coordinate of n is a. So this one's going to be a plus b minus a. But then, of course, this just means a plus b minus a by associative property, right? A minus a is 0, so this is just b. All right, and so for this one, we get that our slope is delta y over delta x. It's going to just be c over b. And look what we've shown, right? So these are the same. If two line segments have the same slope, then they are parallel, right? So our conclusion is that since line segments AC and NM share the same slope, right? And they're distinct and are distinct segments, so they don't share any common points, right? But and are distinct segments. In other words, they're not the same line, right? Then we can conclude that AC is parallel to NM. So the line that connects the midpoints of two sides of the triangle is parallel to that third side that wasn't involved, right? And that's always going to be true. We've proved it now. This might not feel like a general proof because we drew a triangle and we gave it coordinates, right? But we made this triangle is very general. If you change A and B, you can get any triangle that you want out of this, and then you'll be able to just say, right, that this is the benefit of analytic geometry. I'm having trouble saying it, but the benefit of using analytic geometry is that you can compute something as long as you're comfortable working with these variables, A, B, C, these letters, right? You can compute something once and then say that it applies to all triangles, right? So this right here says just a triangle. That means any triangle. So this theorem actually applies to any triangle, and we just computed a proof, basically. It doesn't really feel like the kind of proofs we've been doing, but we computed a proof to show that it must be true. And so we are going to end our proof with a smile.